I see that the number of participants have become stable, so I think it's really time to start the meeting. I first of all wanted to welcome you all to this online EVN Mini-Symposium and users meeting. I should say that we thought a lot of how to deal with the difficulties in holding a meeting in person this year. We concluded that 4 years between 2 EVN symposia was really too much to handle. So we came to the conclusion that we had to do something. We felt it was important to feed the sense of community and give the European VLBI users a chance to meet, to discuss, and show their results. I think it is also important that the feedback from the users reaches all the EVN officers, and I mean the program committee, the board of directors on regular basis. And again, for this reason, it was not acceptable to wait another year for a meeting in person, hopefully, and keeping our fingers crossed. So in the light of this, we also wanted to make sure that this feedback can be delivered. And for this reason, we also made our best to ensure that even in this different format, we could hold an EVN users meeting. So we will see this afternoon how this will develop. For this reason, and considering all these difficulties, I really want to thank you all for joining us, so numerous, even in this unconventional format for an EVN symposium, which really benefits a lot from the face-to-face interaction. But we do what we can, and I think it's great that we are here, so many of us. And I thank all of you who have contributed with the presentation and with the poster, because we have put together really a very interesting and promising meeting and program. So I really wish to thank you all. Before leaving the words to Denise, I know that thanks are usually made at the end of the meetings, but I really want to thank Denise now for all the work that she has done and that she's still doing. I mean, this would have not been possible without her. So Denise, really thank you very much. And I leave it to you now.
Well, thanks very much for those warm words, Tiziana, greatly appreciated. And I'd also like to give all of you a very warm welcome to this EVN Mini-Symposium. We hope that the talks and posters will give rise to rich discussions. During the scientific sessions, which are about to start, we ask that you submit your questions about the talks through the question and answer facility, either during the talks or just after. We'll get to as many of the questions as we can, but it may be that we won't have time for all of them. But don't worry, if we don't get to your question, if you have remaining questions or comments about a particular talk after the question period is over, please feel free to continue your discussions using the Discord server. So the Discord server is separate from this, and it can be used for discussions throughout the meeting. So it's a good way to make contact with the speakers and also with others who may have similar interests or issues, questions on their minds. If any technical issues or other questions arise, you can send email to the EVN Symposium 2021 email address, which is evnsymp2021@ucc.ie about this, and your question or problem will be directed to whoever can answer it. It's best not to send such questions to the panelists through the chat, because they need to focus on ensuring that the talk presentations run smoothly. And we'll be keeping an eagle eye on that email address, so don't worry, your questions will be answered quickly. And I think that's all I'd like to say at the moment, and we might as well get things started. So I'll hand things back over to Tiziana, who is going to chair the first talk session, AGN 1.
Okay, thank you, Denise. I also wish to thank Marco for helping in chairing this session because of this unconventional format and because of the discussions, which I expect to be numerous. It's really necessary that two people are careful and have a look at things. So during this session, I will give, if the speakers are okay with this, a 5 minutes warning before the end of their talk, so that they know. I will try to, I don't know, either, I mean, I will just tell this. So be careful about this. And I also really ask you to please keep the time you are allocated, because it's important that we can run the meeting smoothly and with no with no delays. It's really in the interest of everybody. So our first speaker now is Yuri Kovalev. His presentation is geometry transition as a common effect in nearby jets of active AGN. And Yuri, the floor is yours, and thank you very much.
Thank you, Tiziana. I trust that you can see my screen and you can hear me well. Okay, so colleagues, the first, I truly feel like, so Tiziana has thanked Denise from the Scientific Organizing Committee. As the first speaker, I truly feel like I must say thank you very much, Denise. Спасибо вам громадное for this absolutely fantastic organization of the meeting. Yes, it has just started, but you can already tell how wonderfully it is organized and how deeply you have thought everything through. Thank you very much. Okay, in this presentation, I will discuss today results of a search for geometry transition in a large sample of AGN jets. And so since this is the first talk, I still believe that I don't have to introduce very long baseline interferometry to you, as well as different VLBI networks. However, let me start from discussing a model of a quasar or active galactic nucleus or a blazar. There are different flavors which will be discussed at this meeting, but just basics, right? So we believe that in the middle of them, there is a supermassive black hole, which is fed by an accretion disk, and about 1/10 of the matter is accelerated away from the central nucleus in the form of narrow collimated jets. So what is important for me in this talk is this region, and I will mostly focus on this accretion and collimation zone at the start of the jet. It is believed that the jet starts magnetically dominated, and then around this region it transforms to be dominated by particles. The first example of studying these properties of accretion and collimation zone observationally by measuring its geometry is very well known case of M87, right? So M87 is bright, is close to us, so wonderful angular resolution of VLBI transforms into absolutely fantastic linear resolution for nearby cases like M87. And this was originally the work by Asada and Nakamura in 2012. And here I show to you a plot from an updated plot from Nakamura 2018. Let me go into details here, because this is kind of an analysis which I will discuss today in the talk in details, right? So this plot on the horizontal axis shows to you a distance from the central nucleus, from the central supermassive black hole to a given place in the jet. And on the vertical axis, you see the jet radius. So according to Asada and Nakamura in 2018, the jet in M87 starts parabolic. So it shows parabolic shape with the jet radius dependent on the distance to the power of 1.6, and then changes to the power of about 2 here. So it transitions from parabolic shape to conical shape around the Bondi radius distance, around at about the place of the HST1 region. And what is very important here, and observationally, it is a very difficult task to measure acceleration or deceleration of jets in active galactic nuclei. So recently, Park et al. In 2019 has actually shown that indeed this acceleration and collimation zone, which is observed as parabolic, does show acceleration of plasma, and then beyond the HST1 region, we see deceleration. Okay, very good. So geometry transition is critical to study formation, and geometry transition in jet is critical to study formation and collimation of AGN jets, properties of the geometry transition and the breakpoint. So in case of M87, it is HST1, allow to probe the mechanism of jet collimation, accretion type, magnetic field, external medium, and even determine properties of the central engine. So it is indeed a holy grail of AGN if you want to understand how jets are formed. So when we started this analysis, which I present to you today, this search, there were mostly targeted studies published. So I already mentioned Asada Nakamura, Tseng, Hada, Nakahara, and there are a few others as well. And we decided to perform the first systematic study on stacked VLBI images for a large sample. So the issue which we were worried about is that if you work on your beloved PET, so just one single case, there is a risk that you might miss certain biases or certain issues with the analysis, because it is indeed quite complicated to measure geometry of jets. Moreover, so when working, so we wanted to use stacked VLBI images for an analysis, and I will explain to you in the next slides why it is important. And we use in the analysis 15 gigahertz VLBA observations of about 350 AGN from the Mojave program. So on this plot, you can see a movie on how the jet, in this particular example, this is the Blazar 1308 plus 326, changes with time if you stack images together. So on the horizontal axis on top, you see the ticks representing epochs of observation, images which we add one on top of another while stacking. And you see how the shape of this jet changes and how its emission covers the whole channel, the whole plasma channel. Okay, now numerically, you can see here how with time, while staking the epochs, the apparent opening angle of the jet and 1308 increases. And so you can see that it has taken us 5 years to cover the whole canal, the whole channel of the jet and measure the opening angle correctly. It might be quite extreme example, but this is a typical case that you must stack in order to get a proper geometry of your jets. How do we measure the geometry? Okay, so we stack the image, we have measured the ridge line, and then we measure the jet width along the ridge line, and then we fit two curves, one representing the profile before the break and another representing it after the possible break. So the power indexes K1 and 2 describe the profile. And let me also underline here that we have introduced this R0 parameter, which underlines the jet. So this is the distance from the apparent start of the jet, which you call the core, to the true jet base. Okay, this cannot be ignored. And actually, if jets show this transition, then they are longer than the conical jet shape backwards interpolation. This should be kept in mind by us guys while performing the analysis. Okay, without further ado, results. So we have analyzed 330 AGN stacked AGN images from a Mojave program. And by an automatical procedure without human intervention, so we run our code on 330 jets, and here is the redshift distribution of all these jets, okay, with median redshift a little bit less than 1. And we have found 10 out of 330 jets with transition. Okay, after we have found them, we thought, all right, fine, they might be true, they might be not. Then we started analyzing their properties, and it turned out that 9 out of 10 are nearby AGN. Just such a wonderful coincidence, okay? And for one out of 10, we just don't know the redshift. So it turns out that all the jets, or almost all the jets, for which we have found the transition by automatic procedure are nearby jets. So this means that indeed, if they are close enough to us, our linear resolution is enough to see the transition. So apparently, the first thing to analyze, to look at, is where does this transition happens? And so this shows to you the transition. So on the horizontal axis, that deprojected jet length in gravitational gravitational radius, and on the vertical axis, this power index. So half is parabolic, 1 is conical. And in blue, I show you our transition cases. And you see that most of them sit around 10 to the 5, 10 to the 6 gravitational radii, with one noticeable example, which was actually discussed in the literature even before us, as the case for which an estimate of the mass of central supermassive black hole was actually claimed to be wrong. And after we corrected for the new announced values, here is what we get. So indeed, 10 to the 5, 10 to the 6 rotational radii around somewhere the boundary radius is what we get for the transition. So physics of the geometry transition, just to summarize, it seems from our massive study that it is common for AGN jets, and we see it if our linear resolution is high enough. The accretion and collimation zone we have analyzed within a model is within the boundary radius. At this distance, air collimation with a shock occurs in the jet and converts much of the internal energy into the kinetic one. Parabolic expansion with acceleration transits into the free conical expansion. And important point, which is a result of our model analysis, is that the external pressure plays an important role in this transition. It cannot be neglected. It affects the geometry very strongly. We can perform additional observational tests coming from model predictions. So one test is regarding a shock. So it is predicted that a shock should form in the transition point. And here is our statistics. In Mojave, knowing nothing about geometry transition, not thinking about at all, just performing this typical routine but complicated kinematics analysis, we have found out that only 1/5, 20% of our jets show robust standing features somewhere in the jet. At the same time, half of AGN, which we have found to have geometry transition, have standing features as a result of Mojave analysis around the breakpoint. So indeed, the breakpoint is the region where, with high probability, from the model we expect the shock, and from observations we do see a standing feature. Very nice independent confirmation.
Moreover, you have 3 more minutes. 3 more minutes.
Thank you, I'm doing fine. Fitting for the non-zero distance between VLBI core and jet apex. You remember this parameter R0, which I discussed earlier today. So this the value of this parameter agrees wonderfully with core shift estimates, which can also independently estimate this parameter. And predictions. So you see here one of the examples of a strong acceleration within this acceleration and collimation zone for this 10 AGN. They do agree with Mojave acceleration measurements. However, direct comparison is very challenging because of the resolution of quite poor still resolution of this region. After getting this result, we have started a dedicated systematic follow-up study. And we have selected about 30 AGN with low redshift, and we have observed them. We are observing them right now. Width will be at 2 and 20 centimeter, and so we will get stacked 15 gigahertz images. We will get kinematics, and we will finish these observations in late 2021. And we hope, after analyzing on the data, to double the number of cases, the number of AGN for which we see geometry transition. So to summarize, geometry transition, parabolic to conical, is a common effect in AGN jets. It is found systematically for nearby ones. The break happens within the body radius, around 10 to the 5, 10 to the 10 to the 6 gravitational radii from the nucleus. Within the bulk plasma, kinetic energy flux becomes equal to the Poynting energy flux, and the ambient medium pressure plays an important role in the transition properties. Thank you.
Thank you, Yuri, for being perfect and keeping the time. I see that Silke has raised her hand. So yeah. Please, Silke.
Thanks, Tiziana, and thanks, Yuri. Yuri, concerning the changing the form from conical to parabolic, how do you make sure that you not mix up with precession? The one source where you show that the jet channel is filling up is 1308 at the beginning of your talk. For this, we had a publication where we show this is precession. So you get the same effect if because of precession, the jet fills up if you stack the images. So how do you make sure that you not mix up the different phenomena like precession and changing the form from conical to parabolic?
Thank you. So I would comment on two things here. So number one is regarding precession, right? So you interpret the results of observations from 1308 as precession within the Mojave program from our analysis. We interpret this as plasma instabilities within the jet cone, so that at different times we see different parts of the jet being illuminated. And because of that, this might look to you like a precession, but we believe that in reality, these are just different parts of the jet are illuminated at different times. And that is why stacking is so important. However, talking about 1308, I would like to show to you that this is not a jet which is selected by us as having the geometry transition. So it did not show that.
Okay, okay, that's good. But if all the modeling works and shows this is precession, I mean, then you can still talk that it looks like instabilities, but in reality it can be precession. So I think you should be careful here and take these cases out of the stacking analysis.
I would worry very much if I take out a case from an analysis because of a physical interpretation, which can be one today and another tomorrow. With precession, yes, the worry is that the period of precession is quite low, right? So physically, it's quite complicated to make. But still, I underline that so far it was not shown that precession might mimic the geometry transition observation, right? So you have a precession, if you have a precession, and then you get the transition from parabolic to conical. I don't think that I have seen these examples discussed by anyone. So if you can comment on that, it would be interesting.
Yeah, I think physical reality should go first. And if you have cases where there's good indication that this is precession, then I would just take them out of the sample. I mean, the effect of conical to parabolic is interesting in itself, but there are similarities and should make clear that it's really this effect you are looking for.
There are a couple of questions on the chat. I would stop this here. Thank you, Silke. And there was one question from Sandor. He asks if there is a selection effect causing your sources to be nearby ones. More specifically, he writes, I mean, with distance, the sensitivity to fainter structures may become poorer, and also the time dilation slows down the apparent changes in the observer's frame during the period of stacking.
If you look at this plot of the deprojected jet length versus, or the power index versus deprojected jet length, you can see that we cover quite large distance for nearby ones and for the objects which are farther away. Moreover, in order to test this and to make sure that we have a long enough deprojected jet length traced by this analysis, I didn't spend much time today talking about that. We have complemented our 15 gigahertz data, which are stacked and which are shown here in blue. It's like bluish greenish like color. We have supplemented this data for a number of sources by much more sensitive to extended jet structure 20 centimeter measurements. And we have done it for both the nearby objects and for the objects which are far away. And because of that, we do not believe that here we have any significant bias causing us to better, allowing us to analyzing the nearby AGN jets better. Okay.
Thank you. Well, we have to stop here. There are a number of other questions which you might find in in the DNR section. So Yuri, you have time, and this discussion can be carried out outside. And I ask Daria Zobnina to start her presentation. She's next. And her presentation is about the stacked linear polarization properties of AGN parsec-scale jets at 15 gigahertz. Thank you, Daria. And if it is okay, I will give you like a 3 minutes warning.
Okay, thank you.
Please go ahead.
Dear colleagues, thanks you for the opportunity to present the results of our research. So I'm going to tell you about our research on stacked linear polarization properties of AGN parsec-scale jets at 15 gigahertz. Synchrotron emission from AGN jet is linearly polarized. In the case of odd-red magnetic field, fractional polarization can be as high as 70%. But observations show somewhat lower values. For example, in this case, in the central part of the jet, fractional polarization is about 10 to 20%. The difference can be due to magnetic field disorder and internal and external Faraday rotation. As jet is optically thin, magnetic field tends to be perpendicular to EVPA. So if EVPA image is corrected for Faraday rotation or Faraday rotation is small, we can get magnetic field direction from EVPA image. The goal of our project is to connect variations of magnetic field with its stable component. We used two types of images, stacked images and variability images. Averaging over time, over epochs, so-called image stacking, leads to reduction of noise level. Here are an example of a single epoch map and the stacked map for the same source. This is a stack of 66 epochs. It covers more than 20 years of observations. For on stacked image, noise is about 1.5 times smaller than on the single epoch map. And you see the jet cross section is wider. in comparison to single epoch map. Also, averaging over time gives us an opportunity to get stable magnetic field structure because fast variations are washed out. On the contrary, variability maps give a magnetic field temporal and spatial variations. We made use of rich Mojave-Vilgay program and archival observations data at 15 gigahertz. Our sources were drawn from Mojave sample. All of them have at least 5 full stocks observations between 1996 and 2019. Full sample consists more than 400 AGNs, mainly they are quasars, 1/3 are BLX. The rest are radio galaxies and sources with undefined optical class. Among all sources, the median number of epochs is 10. The majority of sources have less than 50 epochs. The median cadence is about a half a year. So we have the following stacking procedure. First, single epoch images of Stokes parameters E, Q, and U are convolved with a circular beam and aligned by the core position. Then single epoch polarization flux maps are made and corrected for Raytheon bias, accounting for non-Gaussian behavior of polarization noise. The third step is to make a single epoch fractional polarization and polarization direction maps, and finally, as averaging over epochs, stack the total intensity polarized flux, fractional polarization, and EVPA maps are constructed. And also relative variability maps are made. Here is an example image, of image of typical 4-hour sample source. This is a stack of 15 epochs. And you see that in the jet, fractional polarization is about 10-20%. The EVPA in the jet more or less aligns with the ridge line, and they become transverse at the edges, jet edges. So we analyzed the offset between EVPA on ridge line and the jet direction traced by the ridge line. For quasars, we got this histogram, which shows median difference between these angles. Here is the peak at 90 degrees. So EVPA is perpendicular to ridge line. And this is an image for typical for this case source. So along the ridge line, EVPA is perpendicular to the ridge line. This means that as Faraday rotation at 15 gigahertz is small, magnetic field is parallel to jet direction. This could be interpreted as an evidence of helical magnetic field, which gives this polarization direction for large pitch angles. For BLX, we have different situation. The majority of sources have peak at 0 degrees, so EVPA aligns with the ridge line. Here is an example. Along the ridge line, EVPA more or less aligns with it. This result was found earlier in Gabuzda and 2000. We have this result for larger sample. That EVPA aligns with jet direction means that magnetic field is perpendicular to it. And again, the possible reason could be that the helical magnetic field, which gives this such kind of EVPA for smaller pitch angles. Another result is related to variability of fractional polarization versus its stacked values on ridge line. Correlation analysis shows that for the majority of sources, variability of fractional polarization anti-correlates with its stacked values. This means that as fractional polarization increases along the ridge line downstream of the jet, its variability decreases, which means that the magnetic field regularity increases downstream the jet. Next result concerns EVPA variability along ridge line. We found that the typical pattern for EVPA variability is that it decreases along the downstream the jet, along the ridge line, as you can see on these three examples, which also means that magnetic field variations decrease downstream the jet. And here is my summary. A variability of fractional polarization and the EVPA favor a jet model with the magnetic field becoming less variable and hence more ordered further downstream from the core. We confirm earlier results by Gabuzda et al. 2000, but on a higher level of significance due to larger sample that EVPA aligns with the jet for VLAC object. For quasars, on the contrary, EVPA is predominantly transverse. Thank you for your attention.
Thank you very much, Daria. Are there any questions for Daria? I don't see yet. So, Denise, please go ahead. I knew that you were going to ask a question.
No, this is very, very nice talk and a very nice way to show your results. I just wanted to point out, I think in 3C454.3, if you can show your stacked polarization image for that source near the beginning. Can you go back to that slide?
I'm showing it.
Yeah.
Do you see it?
Yeah. That's beautiful, beautiful. One of the nice things that shows up here is a clear increase in the polarization towards the edges of the jet. And that is also something that may come about because of a helical magnetic field. And it's quite beautiful that it shows up so clearly in the stacked images.
Yes, so it's nice. We are studying it at the moment.
Yeah, no, that's excellent.
Are there other questions or comments for Daria?
I see Andrei that has the raised hand, so he can talk now.
Sure.
Andrei Lovanov, if you want to make the question, you should be able to unmute yourself now.
I think he had his hand up from the previous session talk.
Okay. Well, actually, I don't see this. I mean, other people raising hands. I see probably only those who are, you know, logged in the same way I am logged in. I actually have a question that was also, I mean, it's really very basic one. I haven't really dealt with, I mean, this type of science for a long time, but how is the stacking procedure in practice carried out? Daria?
The procedure is written on this slide. So first we make single epoch images, and then we just averaging over epochs in. So in each pixel we find the average, the mean over epochs.
Okay, and how much do you gain in the significance of the signal?
The reduction of noise is about several times.
Thank you. Okay, let me just wait 1 second to see if other people have questions for Daria, and we can move. I see Silke, okay.
Yeah, I've questioned whether one or a couple of sources maybe stood out. Are there examples which are really different from the others? Where you say it cannot be explained with a typical Bialak or the typical quasar phenomenon. So is there some peculiar source maybe?
Yes, probably there are some peculiar sources, but the goal of our study, the main goal at the moment is to make statistics, to give statistical conclusions.
Okay, thanks.
I see that there is a question from Lizakov.
Yeah.
I apologize, but sorry.
Yeah, there's a question.
Yeah, sorry, I see it now, sorry.
Yeah.
He asks how robust is the stacking to the EVPA calibration errors.
We estimated EVPA errors by simulations, and they include many sources of errors, so I think they are robust.
Thank you. Okay. Denise, is your hand a new one?
Yeah, I just want to say in relation to that last question that one of the nice things about this stacking is that if there are small errors in the EVPA, they should average out. So it's much better than depending on just one epoch, which may have an EVPA calibration. Yeah, it's another strength of the technique.
Thank you, Denise. Okay, so I see no other questions, so I would just move to the next speaker, Florian Roesch, locating the gamma ray emitting region in the Blazar 4C 01.28. Again, I will give you a 3 minutes warning before the end of your presentation.
Okay.
Thank you.
Yeah. Hello, I'm Florian Roesch, and I'm a PhD student at the chair of astronomy at the University of Würzburg, working in the group of Matthias Kattler. And today I want to talk about the radio gamma connection in the case of the Blazar 4C plus 01.28, and where within these blazars gamma ray emission is produced. Okay, blazars represent the largest population of extragalactic sources in the gamma ray band. But, however, it has been an open question where the gamma ray emission is produced. So there are extensive studies of correlated radio gamma properties, and there are sample studies. And one of this will be shown in the next talk, I think. And there are also studies on individual sources, as we did for 4C plus 01.28. And however, the location of the gamma ray emitting region is still under active discussion. So on the one hand side, intraday variability of the gamma ray light curves indicates a compact emission region near the jet base. And therefore, the gamma ray emission is typically explained due to external Compton scattering of photons from the broadline region. But in this case, there should be a strong cutoff at very high energies due to gamma-gamma absorption. On the other hand side, there is no evidence for such a cutoff in observations. And VLBI observations show newly ejected jet components that could be associated with bright gamma ray flares, which indicates that the gamma ray emitting region should be located beyond the broadline region. Okay, and to test where the gamma rays are produced, the Blazar 4C plus 01.28 is a perfect target, since the publicly available 2-month spin Fermi-Lab gamma ray light curves show high variability with bright flares. And this behavior is also shown in radio light curves, which I will show later. And therefore, we analyzed 51 epochs of VLBA observations taken at 43 gigahertz during a period of 9 years, from April 2009 to December 2018. And to analyze these data, we loaded the fully calibrated and imaged visibility data provided by the Boston University Blazar monitoring program into DiffMap and fitted them with Gaussian components, which is shown here. And these images show at the beginning of the observation period one bright feature at the center and a faint jet component into the northwestern direction. And while the faint jet could be fitted with one component as two, the bright feature at the center could be fitted, mostly be fitted with 2 or 3 components, the core component and 1 or 2 jet components. And then in April 2015, a new jet component appears, J4, which moves outwards and appears as bright jet feature in later images. And in February 2017, another new component, J5, appears, which moves outward and appears also as a bright jet feature in later images. So to analyze the kinematics of these jet components, we plotted the distance of the jet components relative to the core component with respect to the observation date and fitted them with linear regression, which is shown here. And here you can see that the newly ejected jet features J4 and J5 are ejected in mid-2014 and mid-2015. Furthermore, we looked at the 2-month spin Fermi gamma ray light curve. And this light curve shows high variability with bright flares in 2011, 2014, and 2015. And the 2 flares in 2014 and 2015 could be associated with the ejection of the jet components J4 and J5. Here the dashed lines represent the ejection times of these components. But 4C plus 01.28 was not only observed at gamma rays, but also at different radio frequencies by ALMA, SMA, and OFRO. And here the different radio light curves at different frequencies are plotted together with a Fermi light curve and the real BA light curve. And all these light curves show similar behavior with a minimum in 2013 and flares in 2011, 2014, and 2015. And the radio light curves show also bright flares in 2017. And as already said before, the flares in 2014 and 2015 can be associated with the ejection of J4 and J5. And because all these light curves show similar behavior, we did the cross-correlation analysis between the gamma ray light curve and the different radio light curves using the discrete cross-correlation function and the interpolated cross-correlation function, which leads to positive time lags, meaning that the gamma ray light curve leads to different radio light curves. Okay, and this results, together with the results of the kinematic analysis, can then be used to determine the location of the gamma ray emitting region using a model in which the flares shown by the light curves are produced when a moving jet component crosses through the gamma ray emitting region and through the different radio cores. Furthermore, we use a model in which the radio core is located where the optical depth equals 1, which means that the location of the radio core shifts upstream with increasing frequency. So if we know the location of one radio core, we can compute the locations of the other radio cores using the core shift model. And then using the model for the gamma ray emitting region, we can use the locations of the different core regions and the time lags to determine the location of the gamma ray emitting region. Okay, to calculate the location of the 43 gigahertz radio core. We use jet geometry, assuming that the diameter of the jet is given by the size of the jet components, and the diameter is given by a power law of the distances of the jet components from the jet base. And yeah, with this model, we obtain a power law index of 0.946, indicating a conical jet, and a apparent location of the 43 gigahertz core of 0.112 milliarc seconds. Okay, this result for the apparent location of the 43 gigahertz core can then be used to calculate the apparent location of the gamma ray emitting region using this formula. And with a lower limit, no, with the upper limit of the viewing angle of the jet of 5 degrees, we obtain a lower limit of the deprojected location of the gamma ray emitting region of 4 parsecs, which is far beyond the broadline region and well comparable to values presented by Max Murbeck et al. For 2 other AGN, and also consistent with sample studies, which will probably present it in the next talk. Yeah, okay, to summarize. We analyzed 51 epochs of 43 gigahertz VLBA observations of 4C plus 01.28, and found 2 newly ejected jet components that were ejected in mid 2014 and mid 2015, and could be associated with bright gamma ray flares. Furthermore, we did the cross-correlation analysis between a gamma ray light curve and different radio light curves measured at different frequencies, which leads to positive time lags, and which means that the gamma ray light curve leads the radio light curves. And with these results, we determine a lower limit of the deprojected location of the gamma ray emitting region of around 4 parsec, which is far beyond the broadline region. And therefore, in this scenario, the external quantum scattering of photons from the broadline region can be ruled out for 4C plus 01.28. But the gamma ray emission can alternatively be produced by synchronous self-Compton scattering or external Compton scattering of photons from the dust torus, or by hadronic emission models. So thank you for your attention, and now I'm open for your questions.
Thank you very much, Florian. Thank you for keeping the time. I see that Andre has raised his hand, so please, Andre. Maybe you are muted, we are not hearing you. Andre, I think you are muted.
Now? Can you hear me now?
Yes.
Yeah, now. Yeah.
Sorry, it's just this bloody button pushes itself twice. Thanks, Florian. I understood, if I understood you correctly, you're trying to associate gamma ray flares with locations of VLBI core at different frequencies. Is that right?
Yes, Yes.
Now,
So
my question is the following then. The location of a VLBI core at a given frequency has no particular physical significance except for the opacity in that particular section of the flow. So I would expect that there should be no connection to gamma ray flares whatsoever. A much better connection would be through a sequence of the recollimation shocks that we've seen in several sources. And those will be spaced at some regular spacing, similar to what you see from this core shift to opacity picture. But opacity in the jet is just a selection of your favorite frequencies. So the opacity in the jet should not cause, well, turning optically thin at a given frequency should not give you a reason to give a gamma ray flare at this particular moment. So what do you say to this?
So gamma ray flare is before the flare of in the radio curves. So we use a core shift only to analyze where the radio cores are located, and then we use a model in which the flares, the radio flares, appear when a component crosses through the radio core region.
Yes, but this is what I would say. It's probably not particularly realistic in this case, because again, that particular region only determined by the opacity of the flow, and there's no physical reason for the jet to flare at the moment when it crosses the point when it's become optically thin at 227 gigahertz or 97 gigahertz. So that's must be some more consideration to this idea. I guess recollimation shocks is much more physical, much more better physical explanation for repeating flares or multiple flares produced by a single jet component.
Okay, so it could also be possible that the flare is produced when the component crosses this stationary feature.
This is what we've seen in several sources, not just, but many authors have actually seen that behavior, and that seems to be viable in this case. And
in this case, the main result wouldn't change very much, because it's then the flare or the gamma ray emitting region is further downstream of the 4 parsecs, which is
true. This is what changes is the reason why you produce it. So producing it because of the change in opacity in the flow is, in my opinion, is not particularly viable. Okay, we should probably take it off somewhere else because it takes time.
Okay, yes, I suggest that this discussion is carried out separately. Are there any other questions? I encourage actually people to ask questions using the question and answer window, because it makes it easier to see who is actually, those who have the questions. I saw that Denise has had her hand raised at some point. I don't know if she wanted to ask a question to Florian.
No, I don't need to ask a question. I was just going to comment that, sorry, my printer, my husband just decided to print something, so there's background noise.
Stop in a second.
It'll stop in a second. Sorry about that, folks. No, I just wanted to comment that I agree with what Andre has said, but I think that using the position of the radio core as a general way to compare what's happening in the gamma and the radio is not completely crazy. Basically, it gives you an idea of where down the jet things are happening in the different bands. So maybe it really is this recollimation shock, the standing feature, that may be a recollimation shock that's relevant. But looking at the position of the radio core is also not crazy.
Okay, thank you. Are there any other questions or comments for Florian? Okay. If not, we have now a 20 minutes break just to sort of get up and move ourselves a little. We will be here again at 11. The speaker at 11 will be Ivan. I really ask you to please be on time so that we can start the next part of the AGN I session timely. Thank you.